Welcome, everyone. I'm going to be talking about Schmitty the Solver, which is a project that I've been working on as part of my my ongoing abilities to use Agda to verify neural networks. And Schmitty, in particular, offers you SMT solver integration for Agda in hopefully as modular a way possible. Schmitty, in its current form, has already received a large amount of contributions from Ulf, who is, of course, our expert on, I guess, Agda's reflection mechanisms for sure. And hopefully soon, if you're interested in this sort of stuff, it will have received contributions from you, because there's a ton of interesting stuff that we could be doing that is all very low-hanging fruit. And there is some stuff that would be extremely interesting that is a bit difficult, but we'll get to that. OK, cool. So what is Schmitty? Let's solve some stuff. Cool. Now, I've imported here, there's some import statements, theory for integer arithmetic, and I've put up a few equations. So we have commutativity of plus, we have associativity of plus, we have some sort of distributivity-ish operation here. I think one of the things is already filled in, but otherwise this should more or less map to distributivity. And we have the proof that there is a zero. Actually, there's an actual zero in there, so yeah.
Can I ask a question?
Yeah.
Does this produce a proof, or is it just saying it's OK?
We'll get to that, but for now, at least, this is some sort of reflection tactic that calls out to Z3, and right now, in the simplest case, it inserts a postulate which is called because Z3. So yeah, right now it just says, oh, well, we've externally verified this. There are some cases in which the proofs actually compute, thanks to Ulf. And we're hoping to actually be able to integrate actual Agda programs as a result of this call out, because SMT solvers can generate proofs, but I am getting way ahead of myself. So let's pretend I didn't say anything, and we'll get to that later on. So looking at these solve Z3 things, you might wonder, yeah, but what if I try to prove something that's not true? Like, what sort of horrid error message will I be faced with? And not to worry, the error messages aren't too bad. So let's say we try to prove that if x is smaller or equal to y, then x is equal to y. So that's probably not true. I'm not entirely sure about orders and equality, but I think that's not true. And so if we ask Z3, then it says, actually, it's not true. And I have found a counterexample. And the counterexample I found here is that x is 0 and y is 1. And if you look at these formulas, then you'll see that that is, in fact, not true. I've, of course, chosen a very specific and complicated example where it's really nice to have this counterexample, because it's hard to see from the formula why it's not true. But you could imagine simpler things as well. So this is actually really nice that Z3 actually tells you, like, at least it gives you one counterexample for the thing that you're trying to solve, and it just immediately tells you, no, that's not true. So not only is this useful for verifying, but also imagine you are giving some proofs about integers. You could use this to quickly check if it is actually true before trying to write down the Agda proof, although eventually I hope that you wouldn't have to write it at all. OK, so I've been talking about SMT solvers, and I think I've mentioned Z3 a couple of times. Everything I say in this talk generalizes away from Z3. Just forgive me. It's just the one that I tend to use the most. But equally, any SMT-LIB compatible solver we can use. And I just said SMT-LIB. So what actually is a SMT-LIB? What does it give us? So I'm not an expert on SMT-LIB, but it more or less gives us, it's more or less its specification for SMT solvers, which is more or less solver agnostic. So there's some places where it just goes, the solver can do whatever they want here. But mostly everything that you do should work across solvers. And it gives you a Lisp-like language that you can use to talk to the solver. So you tell it what problem you want it to solve, and it gives you an answer in the same language. And it specifies theories that the solvers are supposed to implement. So that's a minimal subset. So every solver should at least implement this. And that's stuff like arrays, integers, reals, blah. You see the list. There's a list on the slides. And it specifies logics quite opportunistically. So a logic here in SMT-LIB lingo, it's basically a subset of a theory for which there is presumably a more efficient algorithm. And so if there is a well-known, very efficient algorithm for a subset, for instance, there is the subset of the very general logic of reals and integers, which is called quantifier-free linear integer arithmetic with equality and uninterpreted functions, because, yep, why not be not specific? Or if you're a robot, it's called QF-UFLIA. So presumably, there was a well-established algorithm for solving that. That was a lot faster than the general case. And so that's been codified as a logic. Now, we won't really deal with logics, but that is actually a feature I would like to add to have more control over what logic is used. The most important things are the Lisp language and the theories. OK, so what does Schmitty do? Schmitty is essentially an embedding of SMT-LIB in Agda. And by SMT-LIB here, I'm referencing to the Lisp-like language. And it has integration with Agda reflection, where sort of we decide which Agda definitions from the standard library and from the Agda primitive libraries correspond to which SMT-LIB constructs. And then there's the actual integration with solvers via system calls. But that latter, that's the only bit that's not written in pure Agda. But fortunately, that's the system call extension, which was implemented in Agda 2.6.2. The of course, existing release of Agda. Wait, has that been released yet? No? OK. But anyway, so if you use the head version of Agda, you're sure to have that extension. And honestly, system calls are probably general enough that if you want to extend Schmitty, you won't have to touch the Agda code base at all. You can just write pure Agda. So that's neat. So what is Schmitty? Well, it's like I said, it's an embedding of SMT-LIB. And so we've got like a term data type for SMT-LIB terms, which is very simple. It's just propositional logic, predicate logic. I think it's propositional. No, it's predicate. Ugh. Anyway, while I get my logic straight, you can look at that term data type. So we've got variables, which are obvious. We've got literals, which depend heavily on the theory. We've got amplification with some primitive identifiers, again, depending on the theory. We don't have lambdas, and we do have universal and existential quantifiers. So that is all. Except the embedding of SMT-LIB that we're using is well sorted by construction. So everything gets a little bit more complicated. But everything that just appeared is just to make it well sorted by construction. Sorts, I should mention here, are essentially the types for terms in SMT-LIB. So common sorts are the sort bool and the sort int and stuff like that. And there isn't usually, at least in the core theory of SMT-LIB, a function sort. So identifiers have a very specific signature sort. Let's see. Yeah, I mean, I'm not going to explain the intricacies of this data type. Just this is a well sorted by construction embedding of the data type we saw on the previous slide. And it's all fairly standard. And I'd be happy to answer questions about this later. So we've got terms, and terms are just predicate logic, like I mentioned. Then we have commands and scripts as well. Now, scripts are basically just lists of commands. And for commands, we very specifically target a subset of SMT-LIB because it is quite kind of a humongous language. And so we're sort of just adding these on a per need basis. So right now we have the set logic command, which allows you to specify what algorithm you want to use for solving. We have a declare const command to introduce a top level variable. So you can say something like declare const and then the Boolean sort, and then you will have a Boolean variable available. We have assertions, which you just give a term and you tell that's telling the SMT solver to check that assertion. And then we've got the output commands, checksat and getModel. And checksat tells the SMT solver to go and check if the whole set of assertions is satisfiable. And getModel instructs the SMT solver to also return you a model for the particular set of variables that you've declared with declare const. Except again, this embedding is well-typed by construction, so it gets significantly more complicated. So here we have added a bunch of type level parameters. Now the gamma is the context in which the terms will be typed. So this is all the variables that we already have available before we start adding the new commands. Then we have delta. The difference of gamma is the new variables that become available as a result of the command. So that only really plays a role for declare const. And then we have the delta xi, which are output contexts. So they determine what sort of output the script is going to give you. So checksat will give something of type sat, and getModel will give you a well-typed Agda model with an entry for everything that was currently a variable. And then scripts just make lists of commands work by propagating everything as needed. So what do we have? We have terms, commands with assertions, and scripts, which are just lists of commands. Cool. And then what we have is a whole bunch of theories. So the core theory of SMT solvers is just Booleans and the standard Boolean operations. And this is sort of what it's like to implement a theory in Schmitty. So here we declare the sorts of the theory, which in this case is bool. And we declare the literals. Now, for technical reasons, false and true are identifiers. They're functions that you call with 0 arguments. And that's just for very technical reasons. Because in practice, we've chosen that literals in theory should be literals in Agda as well. So natural numbers can, for instance, be mapped to literals here. But Booleans not, because they're not primitive. They're primitive, they're not literals in Agda. And then we have core identifiers for the theory here, which are false and true and not in all the standard Boolean stuff. And then what you specify is you specify the value. And the value mapping is a mapping from all your SMT sorts back to Agda types. So there are types that go in to SMT, and they're often a little bit more complicated, and that's all reflection stuff. So we say, if we've got this thing, the top type, for instance, in Agda, we map that to Boolean true. And then there are types that come out, and that mapping coming out is specified by value. Now, value here maps bool to set, and the thing there is slightly more complicated due to like us avoiding type and type, because obviously set is not of type set. But I decided to hide that for you don't need to know that. You can check out the code; it's not that big of a difference. So what else do we have? Well, a very common theory is the theory of ints. So there's a bit of an awkwardness in designing these things because in SMT-LIB, everything extends the core theory. And so I've chosen to do that by literally having these core constructors, which reference back to the core sorts and core literals. And so here we have either a core sort or the integer sort, either a core literal or a natural literal. And then the value mapping on the way back maps core sorts to the core values and maps the integers back to Agda integers. And then identifiers are either a core identifier, or they are equality, inequality, and if then else, which are technically part of the core theory in SMT-LIB, but they make reference to the sort of the theory extending it, and that gives rise to some sort of annoying loop where you're extending the core theory, but then identifiers in the core theory reference the sorts for the extending theory, and I didn't want to deal with that. So when you build a theory, you just have to deal with it and implement equality, inequality, and if then else. And if anyone has a nice solution for this, I am very welcome to suggestions on this. And then it just has some integer arithmetic. So wait, why is not there? Oh, I just randomly changed that. Negation on integers, which is obviously written not. The the absolute function and all that sort of stuff is part of the integer theory. Note that we're calling this stuff in the core theory, by the way, we're calling it bools, but that's just because we're deciding a theory on bools. We are very much mapping this to Agda sorts so that we can, for instance, decide tuples of equations. Okay, so how does Schmitty? In about 7 steps, and this is really the nitty-gritty of the term conversion, because I'm really hoping that some of you watching will be like, oh, this is pretty easy, honestly. Like implementing a theory fits on a slide, more or less. I could have fun with that regular expression interpreter that Guillaume wrote a while ago and map that to what is apparently the theory for Unicode strings and regular expressions that SMT solvers offer, and reason with that in Agda for fun. Or what other extension you might feel like implementing. Okay, so how does a Schmitty? So there's a whole bunch of steps. So first, reflection. We get the goal of the place where we're calling solve Z3, and that results in an Agda reflected term, which you should not read. It's a horrifyingly huge representation of that nice small term at the type level. So this for all gets translated to this Agda term with all the pies and everything in there. Okay, so far so easy. Then we have specifically, we have a very generic framework for theories in Schmitty, which you can fairly easily instantiate by just giving a few data types. And one of the instantiations is never meant to go to the theorem to the SMT solver. It is actually just meant to make this process easier. And what it is the theory where literals are Agda literals, and the identifiers are Agda names. And so that's one we can very easily translate Agda terms to. So here, for instance, this type gets translated to, we're declaring a constant x and declaring a constant y. We're storing the Agda types for these things. And then we generate an assertion. And note here, we are inserting a negation. So we're actually trying to solve the opposite thing. So here we're saying assert that it's not true, that, and then you have this awful De Bruijn syntax for variables. Because I haven't gotten this to look nicer yet, unfortunately. Assert that it's not true that if x plus y is equal to y plus x. And then we ask for a model. Well, in this case, there is no model that demonstrates that this is not true because it is true. So Z3 will loudly complain at us, and we will catch that complaint, and we will display that as a success. OK, so we've got this sort of raw theory script now. What we do then is we type check the script to see if it is actually a valid script. And this is where all the conversion happens. So as you can see, the Agda name for negation and Agda name for equality are translated to the theory's own names for equality and negation, inequality. I think I have something wrong with all the nots and the negation here, because that's supposed to be a negation, and then that previous negation is supposed to be, this is supposed to be not, and the previous not was supposed to be negation. I'm sure I'll have the other one somewhere as well so that I can complete the triangle of errors. But OK, so we've type checked the raw script and we've converted it to the SMT-LIB specific language. Then what we need to do is we print it as a string. That's all fairly simple. So we come up with some names to give to these things. So x0 and y1, just to make sure that they're always distinct. And while we're printing this, we're actually generating a parser at the same time, which is aware of the variable names that we've generated and their types in Agda, so that we can later do the parsing really easily. Then we do execute it within the type class monad, type checker monad. And Z3 will give us back unsat together with a very grumpy error message about us like asking for models when there are clearly none available. And we interpret that as a success because that is what we want. And then we apply the output parser here. So we turn that unsat into the Agda data type for satisfiability values and the Agda value sat. And That's cool. So now we know that everything is right. We have an actual value again. And now here, we do some magic to turn that into a nice output. So this is what we actually get, Thorsten. This is what we actually get. We do get lambda abstraction here because those are easy to insert. Currently, in some cases, we get this thing that's called because Z3. And then this thing here is added to make it a little bit easier to reconstruct the types. I don't actually show this, but Ulf implemented an extension here where instead of because Z3, you get something that at type checking time, once the lambda arguments have been instantiated, we'll check if the equality actually holds. And if it holds, it reduces to REFL, and otherwise it reduces to this because Z3 thing again.
That's the old proof by authority.
Yes, absolutely. Hopefully,
But
at
you
some point
only
we'll
get
move away from that.
I mean, the key there is you only get because Z3 when Z3 lied to you, right? You have a thing which is demonstrably false, and Z3 said, yes, it's true.
That is true, but that's only true for the theories for which we've implemented those computing proofs.
Oh, yeah,
right?
for sure.
Like, so for instance, for the floating point theories, we don't even have floating point comparison in Agda really, because it's very broken, because it's not reflexive, right? So we don't have a computing proof. We don't have answers that compute for the floating point theory. We do have answers that compute for the integers theory, because all these equalities, once we have constant values, they're just decidable, right? So that's how those work. And hopefully we'll be able to replace them with proofs at some point. Okay, so what else do we have? So currently we have a backend for Z3, which is the first one, which is also why I constantly said Z3 instead of SMT Solver. And we also have a backend for CVZ4. Then we have the theory of integers linked to Agda integers, which is great, and it works really well. And then we have the theory of real numbers linked to Agda floats, which is tremendously unsafe, but very useful in practice. And also, honestly, people who use floating point numbers in practice tend to reason about them as if they were real numbers anyway. So I will use this personally. You don't have to. And like I was talking about on the ZULIP, I think it would be wonderful to link some sort of subset of the theory of real numbers to, for instance, the Agda rational values, or perhaps get a nice representation for real numbers with basic operations working so that we can actually link that to this theory of real numbers, or something like that, something that's more safe and that more people will feel comfortable using. But I'm happy to rely on Z3's proof by authority and pretend that floats are real numbers, even though they really aren't. And then, like has come up many times, we have the proofs which compute. Okay, so that is more or less how the library works and how we've designed it. So now the reason I'm giving this talk, and the reason why I went into so much painstaking detail about how the library actually works, is because I hope that you're excited about this integration of SMT solvers with Agda, and to have a go at writing a pure Agda extension to it. So where to go from here, sort of our roadmap going forwards. So things that are extremely easy to do. If you know any other SMT-LIB compliant solvers that you like, it is extremely easy to add a backend for those. That is almost no work. You can basically straight up copy the file for Z3 or CVZ4 and change the command line arguments a little bit. A thing that we've been talking about is to have a pseudo sort for natural numbers in the integer theory, because natural numbers are, of course, like way more prevalent in Agda code than integers. So reasoning about them would be nice. And we can probably make them a sort of pseudo sort by just whenever we abstract over a natural number, we just also insert the assertion that it should always remain 0 or larger. And that should be fairly simple to implement. Like I said, linking the theory of real arithmetic to Agda rational numbers should be fairly easy, vaguely unsafe, but still very useful in practice, although sometimes you might get incorrect results. There is a theory of floating point numbers in Z3, and that is the theory of floating point numbers, the very icky, hard to understand stuff where you have all this imprecision. And in preparing this, I have like read multiple papers on theorem provers and floating point numbers, and they are a nightmare. But there are theories for them in SMT solvers. Currently, Z3's theory for those is just a bit blaster, so it just like brute forces everything. But there are more interesting algorithms that are being developed for doing so. And so I think it would be very nice to link those to Agda floating point numbers so that we can actually prove stuff about the floating point numbers, albeit by authority. There is a theory of valid Unicode strings as well, which I found funny, and I think it would be fun to link that to Agda. And that theory of Unicode strings also reasons about regular expressions. And like I mentioned, Guillaume has a regular expression library in Agda, so that would be fun. Also, currently, the parsers for the output from Z3, whenever they fail, they just shout fail at you, because I don't know how to use Agda the Agda parser library. If you do, please add error reporting to this library, because I won't be able to do it. And also, I don't really need it in my job at the moment. I can usually put up with the fact that Agda just shouts at me, so that's usually fine for me. And another thing that we've been talking about is if you have a top-level existential, so going all the way back to the first slide, which I should have just copied here, you see here that the last one has an existential. And in practice, this reduces down to because Z3 said so. This is true. But Z3 can actually give you models. And so if we know this is true, we could ask Z3 for the value of Z and generate that as an Agda proof. And we don't need to interpret Z3 proofs for that. We just need the model. And so that is a fairly easy extension where we can actually get some data. OK, going all the way back, but not too far. Yes. OK. A little bit more moderate things are SMT-LIB provides a theory of sequences. And that's some very like high-level reasoning about sequences. But we could quite easily link that to Agda lists, and that would be quite interesting to make reasoning about lists a little bit easier. It provides a theory of uninterpreted function symbols, which would be very useful. But this does require the theory to be extended with a function sort. So there might be a little bit of friction there. I've mentioned the regular expressions. Z3 at least also offers a theory of algebraic data types and reasoning about functions on algebraic data types. I think that would be quite interesting to like take the non-dependent set of Agda types and just let your users reason about all of the non-dependent types in Agda, which is quite a lot, quite useful maybe. There's a theory of arrays, and I'm not sure what to link that to, but I just figured why not axiomatize the Haskell arrays and see what that gives you. And then the more important features are SMT-LIB allows you to combine theories. So if you have two theories whose sort of signatures are compatible, if they agree on the sorting of all the function symbols that they share, then you can merge them and use it as a combined theory. And it would be quite nice to offer that as a, by for instance, just like taking the sum of all the data types that you've provided and allowing you to have combined theories that way. It would make it significantly easier, for instance, to give the theory of reals and integers. And it also allows you to declare logics. And it would be quite nice if we could validate on the Agda side whether or not something actually belongs to a certain logic. So for instance, the linear integer arithmetic logic requires that you only multiply by constants, because those can be unfolded to addition. And then there's a more efficient algorithm. The nonlinear integer arithmetic is not really nonlinear integer arithmetic. It's just you get to multiply by variables now, which a little bit boring in terms of how much nonlinear arithmetic there is, but sure. Okay, and now the thing that I really want, but also really don't have the time to do, and if you feel like it, go for it. Most SMT solvers have this mode where they provide you with a proof of why a certain formula is unsatisfiable. Now, this is unfortunately one of those things where the specification says, and the proof format is completely up to the solver. All that we will require is that it starts with the word proof. So this is why I'm referencing a paper here called Proof Reconstruction for Z3 in Isabelle Hall. It's linked on the event page. And I've tried it out for, I think, I'm not sure what thing this is. I just put something in Z3 and it told me that it wasn't true and gave me a proof. So this is what these proofs look like. And theoretically, we could probably translate this back to valid Agda programs within the type checking monad and then have Agda type check them. And that would give us a very cheap way of actually like giving, I don't quite want to say constructive because I'm not sure if double negation will get in the way. But it will actually allow us to give some sort of proof terms and see what we can do with those. And that would be very interesting, I think.
So haven't people done this kind of thing for Coq as well? Maybe that's a better starting point than the Isabelle Hall stuff?
Yes-ish, if you're referring to SMT-Coq. SMT-Coq does not deal with the SMT-LIB standard. It deals with some quite outdated and no longer actually compiling SMT solvers. So I got SMT-Coq to work on my local machine while like writing all this to like compare it a little bit. I mean,
the general ideas should still be applicable, I guess, or?
Yes, but I think that it might be easier to base ourselves on the proof reconstruction for Z3 for Isabelle Hall, not because it's Isabelle Hall necessarily, but because they're specifically targeting the output that comes out of Z3.
Okay.
Which is yeah.
Is that really sort of a clearly best SMT solver or something, or?
Sorry?
Is Z3 sort of by far the best SMT solver or something like that, or?
I wouldn't necessarily dare to say that, but I think it might be. I think
so, I mean, so it makes sense to target that one in particular, or?
I think it makes sense to target that one. So the problem I had getting SMT-Coq to work was that one of the solvers had stopped updating 5 years ago, I think, and no longer compiled on most platforms. One of the solvers required you to manually patch a few lines of code somewhere before compiling. And also, so all of these were very, very academic projects in the sense that they were hosted on someone's homepage and didn't really super compile. This is recorded, so I shouldn't just like throw shade at some SMT solvers. We could try to target those. And it might be nice to look at the SMT-Coq implementation for this. Because like you said, like the language that they're targeting is a lot more like Agda. But the source language is completely different. So it depends, like probably both useful. Anyway, I think that starts the question round, by the way.
Yeah, I just wanted to say that I'm not sure if Z3 is the best one, but it's at least the most popular SMT solver, I think. Yeah.
I think so, yeah.
Yeah. So it makes sense.
It's also very easy to install as opposed to some others.
Indeed. So, well, which might explain why it's so popular.
I guess I can wait, but I have a question on my mind now, which is very impractical, but anyway. Is it possible, would it be possible in principle to implement Z3 in Agda? I mean, in a way that
so I've not mentioned this, but I should have. If you look in the repository for Schmitty, you find a folder called console, and for their PhD thesis, console implemented first of all a SAT solver in Agda, in pure Agda. And secondly, they implemented essentially eProver in Agda, which is some sort of SMT solver. It's SAT plus axioms that you can specify. And so that is implemented in pure Agda. Now I've heard that it runs basically not at all because it's far too slow. But it is implemented in pure Agda, and what they did was they linked that to an execution of the external tool so that they could get an all good from the external tool. And then if someone asked for a witness, they could start running the Agda one to generate the witness. Now, I'm not sure if this is the most efficient way to go about it, because proof reconstruction might end up being a lot faster in a lot of cases.
But it's a bit of a strange idea. I mean, if you implement a solver, then why would you not always keep track of that you're not lying and not cheating? I mean, and I'm not really sure why this should be so inefficient.
I'm not sure what you're saying. So proof reconstruction in most cases, I think, can be fairly efficient, especially if we just relegate it to Agda.
But if I implement a solver, then it should be certifying, right? It should be a certifying solver, not just a solver which says something and then I reconstruct the proof. But it should just never give a wrong answer, no?
Right. So by proof reconstruction, what I mean is taking the stuff that Z3 spits out and turning it into an Agda proof. So a lot of proofers actually do produce models, right? Some might even keep track of the fact that they're not lying internally. Others do not at all.
Sure.
And they just say yes or no. Yeah. But
as I say, I see what you have. What do you have? Oops, what happened now? Can you still hear me?
You briefly cut out, I think, but you're back.
Yeah, because I'm playing with my earplugs, and then it does something horrible. Sorry. Yeah. So I was just, I mean, wondering whether in principle, I mean, we could do something like Z3, but in Agda. And as I say, I'm not really convinced that it's intrinsically slower. I mean, obviously, Z3 is maybe very highly optimized, but I mean.
I would think that is what Leonardo de Moura is up to. He wanted to have a verified version of Z3. So he's down in the rabbit hole implementing type theory now in Lean. And then when he emerges, he'll probably re-implement Z3 in Lean, right?
Yes, well, maybe we should do an Agda before, no? Somebody, I mean.
Maybe one should say if he emerges, not when he emerges.
I mean, I don't think, by the way, I don't think this classical thing is an issue at all, because I would assume that all these axioms are stable under the negative translation. So
I think so. I think it's just it's a practical problem.
Yeah. Why is it a practical problem?
Just because you have to implement the double negation elimination for like the set of types that you get back out of Z3, right? Or am I estimating that wrong?
I mean, I'm talking about my hypothetic an Agda implemented version of Z4 or whatever, you know. Sure.
I mean, so like I mentioned, there is already an implementation of a SMT solver in pure Agda.
Can you? I didn't understand the name. Can you put the name or the?
The name is Karim Kamso, but the code is about 10 years old, and I've updated the code to compile again under the most recent version, and it is in the Schmitty repository under a separate folder because I am planning to integrate that at some point.
Do you mind maybe at some point to put the name in the chat? So.
I'll put it on the Zulip under Schmitty the Solver.
Okay, that's good. Thank you.
Okay. Any further questions?
Well, there's a trivial question about the command language. I was a bit surprised to see a command language because you would think you basically just give the solver a problem, which is some kind of, I mean, it's just some data structure, basically all the propositions you want to prove.
Yeah, so mostly the command language is used for configuring the solver before you do that. And also there's a difference between declaring top level variables and existential quantification. like in terms of solving, they act exactly the same. Like top level variables are existentially quantified. It's just that the top level variables show up in the model, whereas the existentially quantified ones are hidden because they're under an existential quantifier. And so Z3 is under no obligation to give you an instantiation for them. So, but it's mostly a configuration thing. So stuff like set logic. And there are dozens more of like set this parameter command to like fine tune your SMT solving experience.
Right. So this is directly binding the SMT-LIB interface.
Yeah, I'm more or less completely just implementing the SMT-LIB language as an Agda data type.
Right.
Because I don't just want to use this to use Agda reflection and then insert proofs again. I also want to use this language directly as a target. So for instance, I have data types in another project. I have data types that represent neural networks, and I have functions that compute from those data types representations in the SMT-LIB language that I can then use to query Z3 about properties of the neural networks. And so in such specific cases, it is very easy for me to generate this SMT-LIB data script type. So it's not just to be targeted from reflection, it's also to be targeted by other things that the user might want to do.
Mm-hmm. And a trivial remark, probably these delta contexts could be just in a maybe type.
Probably, but that's a little bit more. I just wanted to be able to use the list concatenation and not have to convert stuff. But yeah, probably they could be a maybe. I've not yet found any reason where multiple things are bound at once. I think technically speaking, declare constant can define multiple constants at once. But yeah, this is premature generalization.
Yeah, I'm saying this because I ended up with a similar story for C commands formalized in Agda, right? You have like a, so maybe you extend your context to, in C, you can always declare a variable, right? And that's the same mechanism. Yeah. Okay, thanks.
Any further questions?
I noticed on the slide about the integer theory, there is something that looks like if then else. What Agda construct does that correspond to? If
good question. Good question. Yes, that's something I wrestled with a little bit. And I don't know how I solved it, to be honest. So let's look at the code. But specifically, so if then else is actually, it's a part of the core theory. And it's something that is implemented in this language. And this language is abstracted over the core theory, meaning that you could instantiate bool as just a type of Booleans, in which case you're just deciding problems on integers.
Okay,
this is not something. So this is not something that comes out as a model. This is only something you can send to the SMT solver. So it will never answer you, I found a solution and it contains an if then else. It will always tell you concrete numbers. So I don't have to turn this back into an Agda thing. And because, yes, that's very, very unclear what that would actually map from, nothing in Agda currently maps to the if then else construct, given that bool is set, given that if you've made bool set.
Okay, got it. Thanks.
I used to do this whole thing where I stratified everything into set and decidable predicates on sets, but it never quite worked out. Right. Any further questions?
I haven't understood. Oh, I haven't completely understood the problem with the if then else. So if I mean bool is prop, I guess you mean.
Bool is set here.
Yeah, but it should be prop.
Well, that's actually a fair point, but
yeah, but isn't it then that you say if x is true implies one thing, and if x is if not x implies something else? And then you take the conjunction.
Let's see. So what would this say in Agda? It would say if this type is inhabited,
yeah,
then return this thing.
one,
otherwise, return that thing.
No. If the first one, if it's inhabited, then sigma, and if it's not inhabited, then the else part.
Yeah, which is also sigma, right? Because sigma is the sort here.
Yeah. That's what Andreas Martin Abel just wrote. I didn't know that you're really Martin. Okay. Yes, this one.
Yeah, so that's what that would correspond to. I don't think that's a thing we have implemented in the Agda standard library somewhere.
Okay.
So there's nothing really that like it is possible to map something to this if then else, probably.
Sure, yeah.
For like universes where you can check if they're inhabited or not.
So sorry, can I ask a different question?
Sure.
Does somebody understands SMT solvers?
I mean, there are lots of like bells and whistles to them, and like lots of like different things about them, right? Like tons of different theories and tons of decision procedures, and all of them are different. So the whole of SMT solvers, probably not.
No, not the whole. I think I once heard something and then I partially understood it, but forgot it in the meantime. But they sort of reduce these problems also to satisfiability or something like this. I'm completely stuck. So how do they work?
I do not know.
So,
I am currently a user of SMT solvers and I'm not an implementer.
Yeah, that's fair enough. Okay. Yeah, if somebody could tell me, because I mean, maybe we shouldn't be just use some strange tools, but maybe
we should co-locate the next Agda meeting with Z3 implementers meeting or something.
I'm not sure that's right.
I think it would be much better, like, to not go for Z3 right away and just like, I think I forgot what the name was, but there's Bob Adke pointed this out to me. So if you're here, Bob, please shout out what solver this is. But there is an implementation of an SMT solver in OCaml where you can build your own theories and hook in custom OCaml procedures into the solving.
Mm-hmm.
And so, sorry, Bob is not here?
No.
Oh, well, then we won't find out what it is called unless anyone else happens to know.
That's good. But I mean, yeah, I know that Kuhn Klaassen had a good idea what's going on. Maybe.
I don't think Kuhn is here either.
No, he's not here.
No.
Maybe unlikely to be here. Yeah. I just wanted to know how one would go about to implement Z4 in Agda or something.
Yeah, so I think there are a couple of toy implementations of SMT solvers that you could have a look at. If I find one, because I had a look at some of them.
Yeah.
If I find one, I'll post it in the Zulip as well.
Okay, great.
Okay, any further questions or remarks?
If there's no more questions, we should thank the speaker.
Okay, yeah.
So. I think very nice work. Yeah.
And if you're interested in contributing to this work, then please hit me up on the Zulip.